Swayam Prabha. Digital India. Educated India.
Hello friends. So in the previous lecture we have discussed regarding the inputs required for digital relays for the protection of induction motors, and we have seen that after giving several inputs to the digital relays may calculate itself the digital thermal element function that is available in the digital relay. Then we have discussed the thermal capacity function that is available in digital relays, and we have discussed that normally three methods are used by most of the digital relays to set the thermal element, and these methods are: first is the motor rating methods, second is the generic thermal limit curve method, and third is the user thermal limit curve method. Now, when we use the motor rating methods, we have discussed that we have to calculate three things. First, that is the run state time constant known as RTC. Second, we have to calculate the cool time, and third, we need to calculate the trip time for hot and cold rotor and stator. So, these three things we need to calculate when we talk about the motor rating methods. Now, let us discuss the second method, that is known as generic thermal limit curve method. So, in this method user has to select one of the curve out of the several curves given by standard motor manufacturers or overload or locked rotor curves. So, most of the relay manufacturers, they will provide several curves, normally they provide let us say 40, 45 or 50 curves. So, user has to select one of the curves out of this given or available curves by the manufacturers, and then relay will automatically calculate other things. So, what are the steps to be followed when we use generic thermal limit curve method? So, the first step is that we have to enter the values of full load current of the motor and the value of SF, that is service factor, and then select the desired curve from the available or given curves by the manufacturers. So, this is the first point we need to consider. Based on the curve number which we have selected, the relay automatically determines or calculates and again hides the value of LRA, LR hot, TD and RTC settings. Then the desired curve is selected in such a way that the obtained value of trip time should be less than or equal to the motor rated locked rotor time. So, this is very important point we need to consider. Now, let us see what are the different curves given or provided by the relay manufacturer. So, you can see here on the screen the curve, that is on x axis we have multiple of full load amps are given, and on y axis the time in seconds are given, and several curves are given. So, you can see that here several curves starting from here 1 to 2 to let us say up to maybe 45, these curves are given here. And here one important point is, whenever we increase or whenever we move from one curve to the another curve, then each increase in genetic curve number that indicates the 2.08 second, particularly at 6 times the full load current. So, when you move from first curve to the second curve, there will be an increase of 2.08 second time, and this is at 6 times the full load current. So, therefore, based on this we can select the maximum curve number using the given equation. So, if we wish to select the curve number, then we have to use this equation, and in this equation you can see that whatever value you obtain, you have to select that curve or you have to select lower than that value, whatever curves are given you can select it. According to this equation, that is for curve number, you can see here this equation contains the lock rotor amps divided by full load current and that is squared, multiply by safe stalling time of the motor when motor is in hot condition, this is given in seconds, and divided by the few constants. So, if we consider or if we wish to find out the trip time for rotor, and particularly when the current I is greater than 2.5 times the full load current and it is less than the 12 times the full load current when it falls within this range, and if we wish to calculate the trip time for rotor, then when rotor is in cold condition, then you have to use this equation, that is Tp is equal to 90 into curve divided by I square, whereas when it is in hot condition you have to use this equation, that is Tp into 75 into curve divided by square of I. To obtain the trip time for stator, when cold stator is used, particularly when I is greater than the service factor SF, then you have to use this equation, that is Tp is equal to 2.5 into curve natural log of some value multiply by natural log of I square divided by I square minus SF square. And when it is in hot condition, then you have to use the another alternate equation in this case. So, if I just give you the table, so this table indicates you can see the first column that shows the multiple of the FLA, and this FLAs are given here, right, starting from 1.1 to 14 values, the multiples of FLA that is given, and after that from second column the different curves are given, let us say curve number 1 to curve number 45, but I have shown only few curves, say curve number 1, 2, 3, 5, 10, 15, 30 and 45, and for each curve the time is given and this time is usually in seconds. So, you can see that for each curve, let us say curve number 1, curve number 2 or curve number 15, the time is given, and you can see that here if I consider the last column, that is the remark column, then you can see that the stator model limits that is given and that is up to the FLA, that is up to 2.45, and beyond that when your FLA becomes 2.5 to 14, then the rotor model limits that is given. So, here stator model limits, you can see that that is nothing but the tripping times in this case are for the stator initially when and motor is operating in hot condition, whereas the rotor model limits, you can see the constant C, that is nothing but the tripping times are for the rotor initially at ambient temperature when it is in cold condition. And here you can see that one more point I have given, that is nothing but the service factor is equal to 1.01 A, where this A is an important parameter which is nothing but the trip time of nth curve. So, you can calculate the trip time of any curve. If the trip time, let us say of curve number 45 is available, then you have to multiply with that n and divide it by 45. So, you can calculate the trip time of any particular nth curve with a condition that you have to use the same multiple of FLA while calculating the trip time of nth curve. So, let us consider one example for generic thermal limit curve method. So, let us say that we have 4160 volt 800 HP induction motor which is protected by generic thermal element curve method. The motor data sheet includes the following information. So, rated HP is 800, rated voltage is 4160 volt, rated full load current of the motor in ampere it is 101, and rated lock rotor amps that is also given in ampere, that is 620.4 ampere, and safe stalling time when motor is running in hot condition it is given as 30 seconds, and service factor is also given, that is 1.15. So, with this available data for the motor, we have to determine two things. Number one, what is the trip time of hot stator considering a motor current of 202 ampere, and in second case we have to calculate the trip time of cold rotor considering a current of 252.5 ampere. So, let us calculate the first thing, that is trip time of hot stator considering the motor current that is given as 202 ampere. So, before we start calculating the first thing, let us calculate first the curve number. So, we have already discussed that the curve number equation is nothing but it is less than lock rotor amps by full load current square into safe stalling time divided by few constants. So, here you can see that lock rotor amps that is given as 620.4. So, that I have put here, and your full load current of the motor that is also given as 101 ampere. So, that I have put. Safe stalling time of motor when it is running in hot condition that is given as 30 seconds. So, that we have put. So, by using this we can have the value of curve number that is less than 15.12. Now, my curve number that is always integer. So, we can select the curve number either 15 or any lower value. So, here in this example I have selected the curve number that is 15. Now, let us calculate the first thing, that is the calculation of trip time when stator is used and it is in hot condition. So, in that case we have already seen the equation to calculate the trip time, that is Tp is given by this equation. So, in this equation we need to calculate the value of this I. So, this I is nothing but it is a ratio of motor current to the full load current. So, motor current it is already given as 202 ampere, right. In first case the motor current is given as this value and we need to calculate the trip time of hot stator. So, if I consider this 202 and full load current is given as 101 ampere, then we will have the value of I, that is 2. So, with this calculated value of I, we can put the value in this equation of Tp, that is 2.5 into curve number I have considered as 15 divided by 36 minus 0.9 into SF is given as 1.15, and that is multiplied with ln. I we have already calculated, that is 2 into 0.9 into SF. So, that is also given. With this if you calculate the value of Tp, you will have the value of Tp, that is 465.901 seconds. So, this is for stator and the disk time is 465. So, if I look at this table, then you can see we are interested in curve number 15 because we have considered the curve as the curve number 15, and we have already calculated for stator, and the time comes out to be Tp is equal to 465 for the value that is 2. So, you can say that when we consider the value that is 2 for curve number, let us say here 15, then value comes out to be close to 427, and here whatever we have calculated, that comes out to be 465 seconds. So, which is very close to the value given in the table. Similarly, if we calculate the value of trip time for cold rotor, then Tp is given by this equation we have already discussed, and in that case you can see that the value of I, that is nothing but we can calculate easily by considering the motor current. So, motor current in this case it is given as 252.5 ampere. So, motor current is this 252.5, the full load current is 101 ampere, value of I that comes out to be 2.5. So, with this value if I put it here, then we can have the value of Tp, that is 216 second. So, with I 2.5 for curve that is equal to 15, the value of Tp comes out to be 216. So, you can see that when I consider the 2.5 that is equal to I, and when I consider the curve number 15 for rotor case, the value comes out to be 216, whereas whatever value we calculated, that is also coming 216 seconds. So, both are exactly matched. Now, let us see the third method, that is nothing but the user thermal limit curve method. So, in this method the digital relay allows the user to construct the custom motor protection curve. So, whatever curve we want to construct based on whatever input we give, that is to be constructed, and that we can construct the curves as few as, let us say 5 or as many as 25 thermal limit points we can have, and based on that the relay can construct the custom motor protection curve. If user wants to follow manufacturer specified thermal limit curve, then user that is free to follow that, and user has to enter additional time points along the curve. However, if user does not want this, and let us say this is given in auto mode, then after this the digital relay automatically calculates a smooth thermal limit curve between the entered time points. So, let us see how this can be achieved. So, let us understand this thing with one of the example. So, let us consider an induction motor which is protected using user thermal limit curve method. So, we will use this method. The motor data sheet have following information: rated HP, that is as 3000, rated voltage is 4000 volt, rated full load current is 366 ampere, and rated lock rotor amps, that is 2380 ampere. Safe stalling time at 100% voltage available at terminal of the motor. When motor is in cold condition it is 16 seconds, and when motor is in hot condition it is 12 seconds. The service factor is given as 1.25. So, the motor data sheet also includes, because along with this data the thermal limit curve is also given as shown here in this screen. So, you can see that again in this curve on x axis we have multiples of full load amps, and on y axis we have the time in seconds, and in this curve 3 regions are clearly marked. One is the overload, another is the acceleration, and another is the locked rotor. However, you can see that there is a discontinuity in this curve between the overload and acceleration and lock rotor, this two, right. So, that means you can see that discontinuity I have marked with this arrow, right. So, with this discontinuity let us see how we can have, or how the calculations are to be carried out if we go for user thermal limit curve method. So, if we examine this curve, then we can find that the thermal limit times at various multiples of full load currents are listed in this table. So, what I have done, you can see that there is a discontinuity from this point, and if I extend it, this value comes out to be 4.5, and when this curve of acceleration start, if I extend this point, this value comes out to be 5. So, there is a discontinuity between the multiple of full load amps from 4.5 to 5. So, you can see this 2 points 4.5 multiples of full load amps and 5 that I have marked, and the thermal limit time in seconds are also given here, because there is a discontinuity between these 2 points. Other points are easily available. So, for respective value of multiple of full load current, you can have the thermal time in seconds for each this value. So, this are available, right. Now, after entering auto for some points, the digital relay will automatically builds the thermal limit curve between the two nearest points. For example, if a relay thermal limit characteristics, that is between 2.5 to 4 times the full load amps from continuous curve between 225 seconds and 72 seconds, then the value of TD that can be calculated using time to trip at 475 FLA divided by TA, and TA can be calculated using this equation, where you are just calculating the value of TA by averaging the time to trip at 3 different value of FLA. So, these are the 3 different values of FLA, and you are just averaging it, and by this way you are calculating the TA. Once TA is available, you can have the value of TD, and that TD you can use it here for the calculation of the value of RTC. In this way we can easily calculate the value of RTC using user thermal limit curve method. Now, with this background, let us see what are the other features of digital relays if we consider the induction motor. So, another important feature that is provided or given by digital relays when we use it for the protection of induction motor, that is in terms of time over current elements. So, let us see how time over current elements feature or logic that is given in digital relays. So, time over current logic or elements are given in digital relays to achieve the protection against short circuits. So, if any short circuit occurs, then that can be protected using time over current elements. So, here protection can be in terms of instantaneous or it can be in terms of time delayed. So, let us see how this can be done. So, in digital relay, time over current element settings are normally given in two groups. So, group 1 that contains different curves, 5 curves let us say, and these curves are starting from US moderately inverse curve given as U1, US inverse curve given as U2, US very inverse curve specified as U3, US extremely inverse curve specified as U4 and US short time inverse curve specified at U5. The second group, group 2, that contains again another 5 curves, but that is based on IEC standard inverse characteristic, that is C1, IEC very inverse characteristic specified as C2, IEC extremely inverse characteristic specified at C3 and IEC long time inverse curve specified as C4 and IEC short time inverse curve denoted as C5. So, two different groups are available. It is up to the user that what group you want to select and in particular group what type of characteristic you want to use or whatever depending upon application. Now, if I consider these two groups in digital relays, then let us see what is the fundamental difference between these two groups. So, in all these two groups, the function or element given as name as 50G, which is known as ground instantaneous overcurrent element, 50P that is phase instantaneous overcurrent element, 50N that is neutral instantaneous overcurrent element and 50Q that is negative sequence instantaneous overcurrent element. So, here in all these 4 elements, it starts with the number 50 and then for ground the notation is G, for phase the notation is P, for neutral the notation is N, for negative sequence the notation is Q, where 50 number remains common in all these 4 elements. This indicates that if we wish to achieve instantaneous protection, right, maybe for ground, phase, neutral or negative sequence, then we have to select these elements. On the other hand, if we want some time delayed protection against particular short circuit, let us say 51P is divided, which means that it is phase time over current element, 51G is ground time over current element, 51N is neutral time over current element and 51Q is negative sequence time over current element. So, here again you can see the 51 number is common, which indicates this is a time delayed protection. So, if we want to achieve time delayed protection maybe for phase, ground, neutral or maybe in case of negative sequence component generation, then we have to go for this 4 elements. Other than this 8 elements, we have 67 P elements which is meant for directional phase time over current and 67 Q element which is meant for directional negative sequence over current element and 67 G is also there for directional ground over current element. Whenever we select time delayed operation for let us say this 4 groups, then the tripping time what is given by this 4 elements which are time delayed in nature, that depends on many factors. Let us say it depends on time dial setting what you are going to do in here, it also depends on secondary current, It also depends on time current curves, maybe you can go for US curve or IC curve. It also depends on CT. It also depends on maximum fault current, that is referred on CT secondary side, along with tripping time and reset time TR. So, let us see, if I wish to achieve this curve or this characteristic, then what are the different equations we can use in digital relays. So, if I use modality inverse curve, then for that, to calculate the time of operation of relay, this equation that is used, and in this equation TDS indicates time dial setting, whereas MP indicates multiple of pickup current, which is nothing but the ratio of fault current referred to CT secondary divided by pickup current of the relay or plug setting of the relay. Similarly, for other curves, let us say US curve U2, U3, U4, U5, the respective equations for calculation of time of operation of relays that is given. You can see in this equations the time constants, this are different for each equations, right. Now, one important point is, in actual field it may possible that, let us say I have 3 relays, out of which 2 relays are electromechanical in nature and 1 relay is a digital relay, and I want to coordinate these 3 relays. Then obviously, it is very practical that one digital relay, I want that should be function as an electromechanical relay, so that proper coordination can be achieved. So, if I want to activate the electromechanical logic or unit in digital relay, that is also available in terms of TR, which is nothing but the electromechanical induction emulation reset time. Particularly, we know that when the disk of the electromechanical relay comes to the original position from its fully operated state, then that time is known as reset time, and that for each curve there is equation of reset time that is different, and that you can easily calculate, where in this case equation of TR, the value of M you can select based on this, right. Similarly, for the IEC curves also from C1 to C5, the different equations of the time of operation of the relays are given in terms of TDS and multiple of pickup current, and similarly equation of TRs for respective curve, that is also given if I wish to use digital relay as an electromechanical relay. Now, with this background, let us see one example. So, here in this example I have considered different value of fault currents in ampere starting from 60 to 400 ampere. I have considered CT ratio as 50 by 1, pickup current I have considered as 1, and TDS value is also I have considered or I have taken as 1. So, the first thing is I wish to calculate the value of MP. So, MP is nothing but my fault current referred to CT secondary divided by I pickup current. So, if I just consider the first fault current, which is 60 ampere. So, 60 ampere I have to refer on CT secondary. So, that is to be divided by CT ratio. So, that is 50, and that is again divided by pickup current, that is 1. So, this value comes out to be 1.2, that is this value, and using this value, that is MP is equal to 1.2 and TDS is equal to 1, you can use the standard inverse curve, that is this curve, very inverse curve, extremely inverse curve, long time and short time inverse curve, that is C4 C5, and you can calculate the time for each curve, and you can see these are the times which I have calculated. So, similarly, for other value of fault current, you can calculate the value of multiple of pickup currents, and then you can also calculate the time of operation of relays for each curve starting from C1 to C5. And if I plot the graph of this 5 curves, assuming on x axis I am taking multiple of pickup currents and on y axis I am taking time of operation in seconds, then you can see that these are the characteristic of different curves starting from this is the characteristic of C4 curve. So, this C4 curve is nothing but your long time inverse curve, right. Similarly, you have the characteristic for the other curves which I have shown, right. Depending upon what type of equation you have used, you can select the curve and you can have the characteristic like this, which follows inverse relationship. So, in this lecture we started our discussion with the second method, that is generic method, and then we have discussed the user method, and in both the methods we have seen one example also, using which we found that okay, if we select a particular settings, then using the equations we can calculate the value of trip time. And then finally, at the end we have discussed about the time over current elements available in digital relays. We discussed that two groups are available, one is based on US curve and another is based on IC curve, and for each group different 5 characteristics are also available, and for each characteristic we have separate equations available. So, we can utilize those equations. Thank you.